If you think mirrors are just simple pieces of glass that happen to reflect your face every morning, there's a lot more happening behind that smooth surface. Every mirror begins its story far from the bathroom wall or the dressing table, deep underground, where one of the most ordinary materials on Earth becomes something extraordinary. The main ingredient in every mirror is silica sand, fine white grains made of silicon dioxide. This same mineral forms quartz, and it's the foundation of most glass products in the world. But when it comes to making mirrors, not just any sand will do. The sand must be extremely pure, free from dust, clay, and especially iron, because even a small trace of iron can give the glass a greenish tint. That tint might be fine for a window, but not for a mirror that's supposed to reflect light perfectly and show true colors. To turn sand into glass, factories mix it with two other materials: soda ash, which helps the sand melt more easily, and limestone, which adds stability so the finished glass doesn't dissolve or weaken when it comes in contact with moisture. In some cases, small amounts of other minerals are added to improve clarity or control color. These raw materials are carefully weighed, blended in giant silos, and poured into furnaces that operate at more than 1,600 degrees Celsius. Inside, the mixture melts into a glowing, molten liquid that looks like thick honey made of fire. It's here that ordinary sand begins its transformation into glass. Once the raw materials have melted completely, the liquid glass flows onto a long, shallow bath filled with molten tin. This process, called the float glass method, was invented in the 1950s and revolutionized glass production worldwide. Before this, glass sheets were rolled or polished by hand, often leaving small ripples or distortions. The float method solved that problem because molten glass floats naturally on the denser molten tin. It spreads evenly under its own weight, creating a perfectly smooth surface on both sides. Fire polishing burners above the bath heat the top layer, smoothing it further, while gravity keeps the bottom flawless. As the glass moves slowly forward, it cools and solidifies, forming a continuous ribbon that's flat, strong, and crystal clear. At the end of the tin bath, the glass ribbon enters a long tunnel called an annealing layer. This is where the glass cools gradually to remove internal stresses. If you cool it too quickly, it could crack or warp later when cut. The annealing process can take hours, depending on the thickness of the glass. By the time it leaves the tunnel, the glass is ready to be cut into large sheets, strong, stable, and completely transparent. Next comes cutting. Giant machines fitted with diamond-tipped wheels score the glass precisely, and with a light tap, the sheets break cleanly along the score lines. Each piece is trimmed to standard sizes or specific dimensions requested by clients. After cutting, the edges are ground and polished to remove any sharpness. This not only makes them safe to handle, but also prevents cracks from starting at the edges. The ground edges are cooled with water during polishing to protect the surface from heat damage. Before any reflective coating can be added, the glass must be perfectly clean. Even a fingerprint, a dust particle, or a hint of oil can ruin the reflection. To make sure the surface is spotless, each sheet passes through a multi-stage washing system. Rotating brushes scrub both sides, high-pressure jets rinse them, and hot air dryers remove every last drop of water. The water used here is deionized to prevent mineral spots. When the glass comes out, it's so clear it seems invisible. Now comes the most important part, the transformation from glass to mirror. This process is called silvering, and it's what gives a mirror its shine. First, the clean glass is treated with a chemical solution of tin chloride. This step helps the silver layer stick firmly to the surface. Then, a mixture of silver nitrate and a reducing agent, often glucose or formaldehyde, is sprayed or poured evenly across the glass. A chemical reaction occurs instantly. The silver ions reduce into pure metallic silver, which bonds tightly to the glass, forming an incredibly thin but highly reflective layer. The layer is only a few micrometers thick, yet it reflects over 90% of visible light. But silver is sensitive. If exposed to air or moisture, it can tarnish over time. To protect it, factories add another metal layer on top, usually copper. This is done using an electrochemical process that deposits copper evenly across the silver coating. Once this is finished, the mirror still needs protection from physical wear, so it's coated with special paint. Usually, two coats are applied. The first seals the metal, and the second provides durability against scratches and humidity. The painted sheets then pass through a drying oven, where the paint bakes into a tough, protective shell. Some mirrors use aluminum instead of silver. Aluminum doesn't corrode as easily and costs less. The process is slightly different. Instead of using chemicals, the coating is applied inside a vacuum chamber. A thin aluminum wire is heated until it vaporizes, and the vapor spreads evenly across the glass surface, condensing into a shiny metallic film. This method, called vacuum metallization, produces bright, uniform coatings with almost no waste. Aluminum mirrors are common in cars, compact mirrors, telescopes, and decorative panels. Once the reflective layer and protective paint are done, quality inspection begins. Technicians and automated machines examine every sheet under strong lighting. They look for tiny defects, scratches, pinholes, dust marks, or uneven color. Even a small flaw can ruin the mirror's quality. Many factories use advanced sensors and cameras that detect imperfections invisible to the naked eye. Mirrors that don't meet the standard are recycled or reprocessed. Those that pass move on to reflectivity tests. Special instruments measure how much light bounces back from the surface. A high-quality mirror should reflect at least 90 to 95% of light evenly across its entire area. After inspection, the mirrors are cut into smaller pieces according to their final purpose. Some are made for bathrooms, some for cars, and others for furniture or architectural use. Cutting machines with computerized controls shape them into rectangles, circles, or decorative designs. Their edges are polished once again to remove sharpness. For home decor, many mirrors are beveled along the edges, giving them an elegant, prism-like sparkle. Others are left plain, especially if they'll be framed later. In places where safety is important, like gyms, hotels, or vehicles, mirrors are strengthened. One method is tempering, which involves reheating the glass and cooling it rapidly. Tempered mirrors are 4 to 5 times stronger than regular ones, and if they break, they shatter into small, harmless pieces instead of sharp shards. Another option is lamination, where a thin plastic film is sandwiched between 2 layers of glass. If the glass cracks, the plastic holds the pieces together. These safety features make mirrors safer for public spaces and vehicles. Once finished, the mirrors move to the packaging area. Each sheet is separated by protective foam or plastic film to prevent scratching. Workers or robots stack them vertically in wooden crates or steel racks, secure them with straps, and add corner protectors. Shipping mirrors is a delicate job. Trucks are equipped with vibration pads, shock sensors, and soft supports to prevent damage during transport. Some companies even use smart packaging that records movement and impact data during the journey. From the factory floor, these mirrors are shipped to construction sites, furniture manufacturers, retail stores, and car assembly plants all over the world. Behind all this precision lies a commitment to sustainability. Mirror production has changed dramatically over the years. In the past, silvering was done using mercury, a toxic process that endangered workers and polluted the environment. Thankfully, mercury-based methods were phased out in the 19th century. Today, manufacturers recover and recycle unused silver and copper, reuse cooling water, and choose water-based paints free of lead and harmful solvents. Many plants also recycle broken glass by melting it back into new float glass. New research is even developing eco-friendly reducing agents made from natural plant extracts to replace chemical ones like formaldehyde. Step by step, the industry is becoming cleaner and greener. Not all mirrors serve the same purpose. Some are made for simple household use, while others have complex scientific roles. Two-way mirrors, for example, are coated so one side reflects light while the other lets it pass through. They're used in observation rooms, smart mirrors, and some modern building designs. There are also dielectric mirrors, made not with metal, but with multiple layers of transparent materials that reflect specific wavelengths of light. These are used in cameras, telescopes, and lasers. Rear-view mirrors in vehicles are made from lightweight glass with aluminum coating and often shaped slightly to reduce blind spots. Some modern versions automatically dim when bright headlights shine on them. Even in the space industry, special mirrors are coated with gold or other metals to reflect infrared light for telescopes and satellites. When you look into a mirror, you're seeing more than your own reflection. You're seeing centuries of human invention. The first mirrors used thousands of years ago were polished stones or metal plates. When glassmaking evolved, people discovered they could coat one side of glass with reflective metal and create a clearer image. Over time, the process became more advanced, more accurate, and more efficient, until it reached the highly automated, chemically precise system used today. What we now take for granted as a simple household object is actually one of the most carefully engineered items we own. Next time you stand in front of a mirror, whether you're brushing your hair, fixing your tie, or just checking your outfit, think about where that mirror came from. It started as raw sand in the ground, was melted into glass at fiery temperatures, floated on molten tin, cooled in perfect balance, washed to microscopic cleanliness, coated with layers of precious metal, painted, polished, inspected, and shipped, all so it could hang silently on your wall. Every step requires accuracy down to fractions of a millimeter and control over chemistry, temperature, and timing. A single mistake, a fingerprint, a grain of dust, or a slight change in heat could ruin the reflection completely. The process of making mirrors is a perfect example of how science and craftsmanship come together in everyday life. It combines geology, physics, chemistry, and engineering into something we rarely even think about. From the soft glow of molten glass to the gleam of polished silver, each mirror represents both human creativity and precision. It takes teamwork, technology, and a little bit of patience to turn something as ordinary as sand into a perfect reflection of the world around us. So the next time you catch your own image in a mirror, take a second to appreciate what's behind it. That clear reflection is the result of centuries of innovation, industrial progress, and careful work by countless people and machines. From the earth to the factory floor, from molten glass to shining surface, a mirror is not just glass and metal. It's a story of transformation. What you see in the mirror is you, but behind that reflection is the journey of light, science, and human skill, working together to make the ordinary extraordinary.